Alright, in this video, we study the collection of square integrable functions with period of 2 pi and see that this can be regarded as a vector space with some appropriately defined vector addition and scalar multiplication. And we also define the norm in this space and also the inner product in this space, inner product between functions in this collection. So that in this way we can interpret this collection of functions as some kind of geometric object. Okay, to see that this collection of functions is a vector space over C, that is the set of complex numbers, we need to define addition and scalar multiplication. And let's say f and g are such functions in this set. Then we define f plus g by this equation, f of x plus g of x. So it's just the addition of the functional values. Okay, and let's say any alpha. In complex numbers, we define alpha f by this equation, alpha times f of x. And of course, x is any real number. Well, this is a periodic function, so we can limit this domain between negative pi to pi, but it doesn't matter much. Anyway, addition and scalar multiplication are thus defined. Now, in order to prove that this collection of functions is a vector space, we need to show the bunch of axioms, those that are these. First is this set is closed under vector addition, and the addition is commutative, and it's also associative, and there is a zero element in the space. And for each element, there exists an additive inverse such that this holds. And also, scalar multiplication satisfies this closure condition and this distribution of addition of scalars and distribution of addition of functions and the existence of the multiplicative identity of the scalar and the associativity of scalar multiplication. So these are pretty easy to show. So I don't prove all of them here, but only the first one, this one, closure of addition. Let's do that. Okay, so what we need to show is, assuming f and g are elements of this collection, then we show that f plus g is also an element of this collection. So to show this, we need to show this integral. So this f plus g is square integrable. So that means f of x plus g of x modulus squared dx is finite. So this is our goal. So let's do it. So we start from this, and since f of x and g of x, they are just complex numbers, so its modulus, to its modulus, we can apply the triangle inequality. So this is less than or equal to f of x modulus and g of x modulus, everything squared. So this is by triangle inequality. And just expand this, and then we have f of x squared and g of x squared and 2f and g, everything dx. Then split the integrals. and this one plus 2 f of x times g of x. Okay, now this one, f modulus and g modulus, they are just non-negative real numbers. Okay, so for non-negative real numbers, let's say for any a b that are positive or 0, we have the arithmetic mean is greater than or equal to the geometric mean, right? So let's say and let's say so if a is f modulus squared and b is g modulus squared, then this part is so let's write this first, and so this part is less than or equal to the sum of these divided by 2. So 2 f of x squared plus g of x squared divided by 2. So this is the geometric mean, and this is the arithmetic mean of this and this. So these two will cancel, and we have f modulus squared here, and g modulus squared here and here. So let's combine them together, and we have this and this, g of x. So by assumption, this is finite and this is finite. Therefore, the total sum is finite. Therefore, f plus g belongs to this set. Therefore, this is closed under the vector addition, and we're done. And other axioms can be easily proved. For the details, please see my lecture notes. So now we know that the collection of functions r2 pi squared is a vector space. We can define the length of each vector by the L2 norm, or also known as mean square norm. Okay, suppose f is a function belonging to this space, then its norm, L2 norm, is defined as this. First, calculate the integral of the modulus of that function squared, and then square root. So this is called the L2 norm, or mean square norm. Well, if you compare this norm to the norm of the n-dimensional Euclidean space, a vector space, suppose let's say x is something like this, 1, 2, and up to n. So this is n-dimensional vector. Its norm was defined as this. Its Euclidean norm was defined as this. So sum of I from 1 to n x1 xi squared, and take the sum and take the square root. So they are very similar. So instead of summation, we have integration here. Otherwise, it's all the same. So elements are squared here. And then after taking the sum or integral, we take the square root. So they are parallel to each other in a sense. And in this sum of n-dimensional vector, of course, there are n elements. Okay, but here in the integral, how many elements are there? actually there are infinitely many elements, right? Because this is an almost continuous function between negative pi and pi. So there are infinitely many points at which this functional value squared is calculated. So the dimension of this vector space of functions is actually infinity. So it's an infinite dimensional vector space. And any vector space equipped with a norm is called a normed vector space, or simply normed space. So our collection of functions, periodic functions, square integrable, this is a normed space. And remember the scalar product or dot product between vectors? We can define something similar for this space of functions. And that is called L2 inner product. Here we are considering complex valued functions here. So it's a little bit tricky. But anyway, so f comma g within brackets. So this is the inner product between f and g that is defined as this. The integral f of x and g of x conjugate, complex conjugate, dx. So this is called the L2 inner product. Well, we can define whatever we want as long as it makes sense. So does this inner product make sense? So what do we mean by that? So it means this uh, integral is finite. So let's take the absolute value of this. This is a complex valued function, so the inner product may be any complex number. So let's take the modulus of that, and using this, this is equal to, less than or equal to, the integral of the modulus. So this is another manifestation of triangle inequality, actually. And so we can split the integrand into two parts. So the modulus of a product is the product of the moduli, right? So we can split this like this. But the modulus of the complex conjugate is just the same as the modulus of the original function, original complex number. So this is equal to f of x modulus and g of x modulus. Okay, again, using the fact that the arithmetic mean is greater than or equal to the geometric mean. So this is less than or equal to this f of x modulus squared plus g of x modulus squared over 2. Now, split the integrals. This is equal. And we have actually, so we have, let's use the norm notation. So by assumption, this is finite and this is finite. Therefore, the sum is finite. Therefore, this integral makes sense and this inner product is well defined. And let's compare this inner product with the scalar product between ordinary vectors. So if we have two vectors, let's say x, x1 up to xn, and y, from y1 to yn. So they belong to real n-dimensional vector space, let's say. So the scalar product between these two vectors were defined as this: I from 1 to n, and xi, yi, and sum of this. Okay. So if you compare this with the inner product between two functions, then we take the product at each between each corresponding elements, and then take the sum. Here we take the product between functional values at each point within this range of integration, then integrate. So integration is just a sum in essence. So they are basically the same thing. The only essential difference is that this is finite and this is infinite. And also, if we consider complex n-dimensional vector space, then we define the scalar product as this. So xi and yi conjugate, complex conjugates. In that case, this is more similar to our definition of the inner product. So we can see that this inner product is a generalization of the scalar product between two vectors. And just like any other scalar products, we can prove the Cauchy-Schwarz inequality for this inner product. So if we have two functions, then we have this inequality. So the modulus of the inner product is less than or equal to the product of the norms of each of them. Okay, so the proof is an exercise. Okay, so this is called Cauchy-Schwarz inequality. And again, just like the usual scalar product, we have the following properties for the L2 inner product. That is, first, the norm squared is equal to the inner product of the same function. And inner product between f and g, if we swap the order, g and f, that becomes the complex conjugate of that. And f1, f2 inner product with g is f1 g plus f2 g. So this is kind of a distributive law of inner product. And the same applies to the second component. So f inner product with g1 plus g2 is the inner product between f and g1 plus f1 g2. And also, alpha is a complex number. So alpha is a complex number. It's a scalar. So alpha f times g is alpha f g. And f alpha g is alpha complex conjugate f of g. So all of these should be easy to prove. So they are almost trivial. So it's an exercise. If we use this inner product, the Fourier coefficient of a function f can be expressed very concisely. That is, so the Fourier coefficient ck of function f is just this. 1 over 2 pi and f and exponential of I kx. So to see this, just go back to the definition of this inner product. So that is this integral f of x, and the complex conjugate of this is exponential of negative I kx. So this is the Fourier coefficient ck of f. And the orthogonality of these functions, exponential of I n x, can be expressed as this. E to the power of I n x and e to the power of I m x is equal to 2 pi delta, so Kronecker's delta, n m. So just go back to the definition of this inner product. What this means is this. This E, I, and X, and the complex conjugate of this is E minus I, mx dx. So we have seen that this equality holds. So when n and m are equal, then this integral becomes 2 pi. Otherwise, it's 0. So that's what this means. So it's very concisely expressed. It's nice. So that's all for this video. And in the next video, we study another type of convergence of Fourier series, that is convergence in this L2 norm we have studied in this video. See you later.